thank you again for joining us this evening. You were brought into this session with the microphone and video off. If you have questions, please put them in the chat. Megan will collect them and address them to Ken after his presentation. This program will be recorded and it will be made available on the Detroit Public Library YouTube channel and through Wayne State University's website. I am Jennifer Dye, a librarian at Detroit Public Library. We have offered astronomy programs for the last several years. When things fell apart in spring 2020, we put our programs on hiatus. But we finally launched our astronomy programs on Zoom early in 2021. Over the last several months, we have worked with Megan McCullen, director of the Wayne State University Planetarium, on programs presented by Wayne State faculty and alumni. We're continuing our past practice of presentations by members of local astronomy clubs, but look forward to working more with Megan and the planetarium. Next month's program will be some presentations from NASA and JPL on the science of the James Webb Space Telescope. The Eventbrite link is not yet published, but will be soon. And I'd like to, Megan, can you talk yet? No, Megan usually gives a brief introduction to the astronomy program at Wayne State and cannot today because we're having some problems. I assume, Megan, you are going to put questions in the chat when we're ready for questions. All right. And if we have time at the end, we'll be happy to let people unmute and ask questions directly. And I have your bio, but I didn't get it put in my document. So Ken Bertin is a member of the Warren Astronomical Society, which is where I met him. And he has been sharing his love of astronomy since he was in grade school. He sent me a very nice bio, which I didn't incorporate in my document. So if he has anything he wants to share, please go ahead and share it.
Okay. All right, I'll just give you a brief bio myself. I'm a financial planner by trade. I also officiate sports throughout the Detroit area and Michigan for volleyball and softball and swimming and a couple other events. I have a degree in finance from the University of Arizona. I went to the University of Arizona with the intent to become an astronomer and was talked out of it by a very famous astronomer by the name of G.P. Kuiper. He told me that we'd love to have you in there. He says, but I'm the head of astronomy for the University of Arizona. I make $22,000 a year. He says, get into a business where you can make money and keep it as an avocation, and you can do whatever you want, buy whatever telescope you want, and so on and so forth. And I followed his instructions and became a financial planner after my service in the Army. The Vietnam era, I didn't go to Vietnam, luckily, but I did spend time there, and that also enhanced my astronomy because I took a portable telescope with me to Korea and was able to see many things there as well. So I've been involved with this. I've taught kids at camps and things like that, and I enjoy going to libraries and to schools and all the like. And if you have children that are in school or whatever, the science teacher can get a hold of me, and I'll be very happy to go over there and speak with them. It's as fun for me as I can tell you. And I've told people jokingly that I can answer any question that you ask in astronomy, not necessarily right, but you may not know the difference at that point in time. So anyway, the presentation tonight is about the life and death of stars, or birth, life, and death of stars. I put together about 150 hour-long presentations about the history of astronomy and many of the astronomers. I've given it all over, like I said. I also did a Astronomy of the Week program. Whenever I went to a meeting, I give what was in the news currently, what the new things were. And when I started doing that, there were probably 5 or 6 new things each week. And by the time I stopped doing it a couple of years ago, it was about 80 a week, but I would only have to narrow it down to 5 or 6, as it were, just because of the time factor. We have an observatory out in Ray Township. It's worthwhile going to. We have it on the fourth Saturday of the month. It's a beautiful observatory, 8-inch telescope. We have access to a 22-inch Dobsonian, and lots of other telescopes go out there by members and such. It's a very worthwhile experience. The Warren Astronomical Society meets the first Monday of every month and the third Thursday. Right now we're online with our Thursday meeting, but our Monday meetings are at Cranbrook, and it's a nice big auditorium, so it's some safety involved. And I have a wife and 3 grandsons and a very nice son-in-law, and my daughter is married to this very nice attorney, and the grandsons are 16 and a half years old, and a couple of them, one of them has a particular interest in astronomy itself, and that's kind of an enjoyable thing for me as well. So if you have any questions afterward on anything in that, I'm open for it. But that being said, why don't we get going with the presentation? And let me get it up here. Give me a second here while I set it up. And I think that you have that in front of you, do you not? Wait a minute.
Yes, but not full screen.
How about now?
Now it's full screen.
That's what I wanted. Okay. All right. So the story that we're going to talk about tonight is the life and death, birth, life, and death of a star. A lot of people don't understand that the universe is extraordinarily complex. Many of you probably do because you're keen in on this. It is extremely interesting, and the stars are varying in so many different ways. I will try and illuminate some of that for you. So here we go. We've learned about what happened for the first billion years or so in the history. I have to do one more thing here. This is in my way here a little bit. Let me get that out of there. Okay. Which leaves us with lots of stars and galaxies, and we are now equipped with the terminology needed to describe and categorize these stars. And this is kind of the history of the universe. It believed to have begun with a thing called the Big Bang, and there was just matter in space for a while, and then it started to congeal electromagnetically, and then by gravity and such. And the first stars appeared about 400 million years after the beginning of the Big Bang, which was about 3.7 billion years ago. We're kind of modifying that a little bit because we've learned that the universe is expanding at an accelerating rate. So it may not have been quite 13.7 billion years, but there's a lot of study on that, but 13 billion years is quite a bit of time. And here you have, let us take a look at the elements on the periodic table. You got hydrogen and helium. They were here near the beginning of the universe. So from where did the rest of the elements come? What about all the planets and the moons? How did those get here? The answer to all these questions makes sense once we learn more about what goes on inside a star from the moment they are born to the time of their death. This story varies widely based on the makeup of the stars themselves. What you're viewing here is the Hertzsprung-Russell diagram, where we can locate all the stars by their classification. So there's the thing called the mainstream there in the middle. And that main path is where our sun lives because it is in its regular lifetime. Stars that start to die generally will start to expand to become red giants and such. And most of the ordinary stars, not the supermassive ones, will eventually evolve to a white dwarf, which is a star that is losing all of its capability. It's not necessarily white. It actually goes dark eventually, but it is called a white dwarf. Our sun is a yellow star, classification G2, and the 2 is kind of like the size of it. Let's move on from there. I've got this diagram up here that a supermassive star blows up, and the Crab Nebula is a great example of that, and that's on the left. On the right is the Ring Nebula, and that's what stars eventually will become after they've shrunk to a red dwarf. And all that, the matter is expanded out, and that is what all that colored ring is. We all know that they die, and the type of death along with what's left over. This is all entirely dependent on the mass of the star. These pics indicated the basic results due to the mass of star. Again, on the left is a supermassive star end in a supernova, and which produced the Crab Nebula. And on the left is the star not massive enough to explode. That's like our sun, as I said. Now let's go through the lifetime of a few different kinds of stars so that we understand the 13 billion years of development in the universe. Obviously, the life cycle of any star from birth to death and all the stages in between spans millions or to billions of years, depending on the star's mass. Stars don't seem to change at all because a human lifetime is a snippet of a fraction of a blink of an eye, regardless of the mass of the star. Now let's go through the lifetime of, obviously the lifetime cycle, as you can see, is very interesting in its, again, the path that will be followed by a particular star depends mainly, again, on its mass, or how much gas was collected and collapsed to form the star. This is because the amount of material will serve as the star's fuel. As we may remember from physics and chemistry, when nuclei collide with enough energy as to overcome the electromagnetic repulsion between them, the strong nuclear force takes over and they fuse with a small fraction of their mass, converting into huge amounts of pure energy. Therefore, only by colliding nuclei together and fusing them in its ultra-hot core can a star release enough outward energy to counter the effects of gravity, relentlessly crushing inward. This means that the amount of matter that forms the star determines the amount of fuel, and through a variety of other factors, the lifetime and eventual fate of the star. What keeps a star together is gravity. What keeps the star from collapsing is the thermal nuclear reaction, which is hydrogen fusing into helium. Once that action has run its course, gravity takes over and the star starts to collapse. The result is the pressure begins to increase and the helium starts to fuse. And the word burn works here if you want to use it. And the star again expands into a red giant or red supergiant. As the helium fuses, the star collapses again, producing still heavier elements. The less massive stars eventually dissipate, producing a planetary nebula with a white dwarf at its center, which you saw before, which cools and dies. The highly massive stars continue to collapse, and upon reaching critical mass, which is mostly iron, they explode. The explosion produces many other heavy elements, and the final result is either a neutron star, or in the case of very high mass stars, a black hole. All right, so as said, the earliest era of star formation, the material was mostly exclusively hydrogen and helium, as this was what remained after the brief 17 minutes of nucleosynthesis soon after the Big Bang. This matter collects due to gravity, pushing increasingly inward as it contracts until things get so hot over a few million years that iron fusion eventually begins, establishing an equilibrium and generating a yellow or red main sequence star that glows with all the energy released from the collisions happening inside. Given the mass is the key factor here, let's start with a low mass star. This would range from the smallest that stars can be, meaning the smallest amount of material that can sufficiently trigger nuclear fission so as to qualify a star, which is about 13 Jupiter masses, to a star somewhere in the ballpark of our sun's mass. As we already know, any star will begin as a cloud of gas and dust at least a few light years across. That's the cloud itself, by the way. These fusion reactions begin with two protons fusing, followed by subsequent beta decay to get a proton and a neutron. And we call this a deuterium. That's D-E-U-T-E-R-O-N, which is the nucleus of heavy hydrogen. Then deuteriums are involved in reactions that make helium, which has two protons and two neutrons. Such a star will continue in this manner for billions of years, slowly fusing all the hydrogen in its core into helium and maintaining a relatively steady size, temperature, and luminosity as it does so, until almost all the hydrogen is gone. Here things really begin to change. The core of the star will shrink and get hotter, which makes the remaining hydrogen burn even faster, and all of that extra energy being generated will radiate outwards and push the outer layers away from the core. As the outer layers expand, they cool and thus become more and more red, and the star climbs up the red giant branch until we have a red giant star. The star can maintain this new status for a little while longer, around 1 billion years, but after almost all the hydrogen is gone, the core gets even smaller and even hotter. At this stage, a phase called Helium Flash, things are so hot that the star is able to fuse these heavier helium nuclei into larger nuclei like carbon and then oxygen through something called the triple alpha process. And this means that the star has a whole new source of fuel in all the helium it has been making for billions of years. The star begins pulsating as it runs through its final energy reserve, entering what we call the horizontal branch. And in this time, it becomes smaller, hotter, and bluer until much of the helium has been fused into larger nuclei. Once the core is predominantly carbon and oxygen, with just a shell of helium around it, the shell of hydrogen around that, the star has very little material left to burn. So the core will collapse and the star enters a asymptotic giant branch. This means it will grow rapidly and become a giant star again until the last bursts of energy eject the outer layer, pushing it away from the core and back into interstellar medium, leaving only a tiny, very hot, bare core behind, around the size of the Earth. This will gradually cool as it has no more fuel to burn. Not being hot enough to fuse carbon or oxygen nuclei, it will contract further until all we are left with is a white dwarf star. The ejected shell is called a planetary nebula, which is misleading since it is not a planet and did not come from a planet, but the name originated from the confusion upon its discovery, and it stuck. The material in the planetary nebula will then become available to join more gas particles to form yet another star. And that's virtually what happened to us, by the way. We were probably part of a star that collapsed and such, and that's where you got the Earth, but we'll get to that in a moment. For a high mass star, one's much more massive than our sun, things are quite different. Their demise will not be so quiet. Big stars go out with a bang. Things start normally with a gas cloud collecting under the influence of gravity. It is simply that this cloud will be much larger than those that form low-mass stars, so it will contain much more mass. More mass means more gravity, which means the force pushing inward is much stronger and the star gets much hotter. The hotter temperature means faster fusion, which generates greater outward pressure to counteract the greater inward pull of gravity. This produces a main sequence star that is hot, big, bright, and blue. This is where things start to go differently from low-mass stars. Whereas low-mass stars take billions of years to use up all their fuel, high-mass stars are much hotter and burn their fuel much faster. This means they use up all the hydrogen in their cores in around just a fleeting 100 million years, and even 10 million if big enough. As the fuel starts running out, the core contracts and heats, producing more energy, so the star will swell up and become a giant star, just like we saw in the low-mass stars. However, while the core of a high-mass star continues to compress, it gets much hotter than the core of a low-mass star, and it becomes able to fuse helium nuclei to form carbon, and then oxygen, and then neon, and then silicon, even heavier nucleus being relegated to a smaller and smaller region of the core that is hot enough to fuse it. All the way at the center sits the heaviest element that can be fused within a star, and that is iron. As this occurs in these different layers, each performing a particle-type fusion until no fuel remains, the star is left with a core of iron nuclei that are so stable that further fusion can release no more energy. Here is where gravity wins the fight. The star collapses within a single second, the outer layers bouncing off the core and triggering an explosion, thus ejecting all of the heavy nuclei the star has created out into space. This awesome event, one of the most violent and energetic phenomenons in the universe, is called a supernova. A supernova generates such unbelievably burst of energy that in a brief moment, dozens of elements heavier than iron can also be synthesized. Nickel, copper, zinc, silver, gold, any element with an atomic number greater than 26 is made either in a supernova or a rare event like the collision of two neutron stars, or a neutron star and a black hole, which are objects we will discuss in a moment. That's why these heavy elements are so rare compared to the elements like carbon and oxygen, because stars can't synthesize them the way they can synthesize all the elements up to iron throughout their long lives. Nature only makes these rare elements during the death of a high-mass star or in certain exotic collision events. Supernovae are also so bright that they are brighter than the entire galaxy in which they live. When viewed through a telescope, and if in our own gravity, they can even be visible with the naked eye. With the one, like the one generated the famous Crab Nebula, which recorded by a variety of civilizations in 1054. The supernova did not leave behind a white dwarf. There it is. How's that? Moving on. Lower mass stars that begin with less than about 8 solar masses leave behind white dwarfs, because once reduced to its lighter Earth-sized cores, there is not enough gravity to overcome electron degeneracy pressure. In other words, a white dwarf will become a kind of like one gigantic metallic solid with an electron clouds around the nuclei pushing against each other and preventing additional collapse. This object is very dense, and 1 teaspoon weighing around 15 tons. So below about 1.4 solar masses, the maximum mass of a white dwarf is also known as the Chandrasekhar limit. Chandrasekhar, very interesting guy, by the way, limit. This is the fate of the core of the star. But for high mass stars, where let me just see if we can. There we go. Let's get that in. But for high mass stars, where upon its death the core of the star is above the Chandrasekhar limit, which means it is massive enough for a supernova to occur, one of two things will be left behind. If the core is between around 1.4 and 3 solar masses, Having been generated by a star that was originally somewhere in the ballpark of 10 to 40 solar masses, the core will not be able to support itself against gravity, and it will collapse with such tremendous force that all the electrons get squeezed into protons, such as they can combine to form neutrons, and the shock wave from this event is what triggers the supernova. The object that remains is a ball of neutrons bunched together like one atomic nucleus the size of New York City, containing all the mass originally within the core of the star. A teaspoon of a neutron star could weigh a whopping 10 million tons. A little of an idea, there's your red dwarf star. Let us now review what we just learned about the lifetime of a star. When a star forms from a gas cloud of some mass, which is almost always about between 1/10 of a solar mass and around 30 solar masses, a star produces somewhere along the main sequence. As you saw in the earlier, that was the Shannon star. The main sequence was that line right through the middle of it. As the fuel of the core begins to run out, it contracts, which raises the pressure around the core and pushes the outer layers outward, where they will then cool, producing a red giant. All stars will have a red giant phase when their fuel is almost gone, regardless of their mass. Finally, when the star can no longer perform sufficient nuclear fusion, which counters the effect of gravity, the star will collapse, leaving a white dwarf if it is of low mass, neutron star if it is immediate mass, and a black hole if it is especially high mass. Telescopes in space now get able to see the black holes. In May of 2019, astronomers just managed to take the first images of a black hole, and now the next challenge facing them is how to take even sharper images so that Einstein's theory of general relativity can be tested. Redbound University astronomers, along with the European Space Agency, ESA, and others, are putting forward a concept for achieving this by launching radio telescopes into space. They published their plans in Scientific Journal of Astronomy and Astrophysics. The idea is to place 2 or 3 satellites in circular orbit around the Earth to observe black holes. The concept goes by the name of the Event Horizon Imager, and in this new study, the scientists present simulations of what images of the black hole, like Sagittarius A, would look if they take satellites like this. And by the way, we just recently had a picture of that black hole in the center of our galaxy, which was very, very, very cool to look at. But again, there isn't a whole lot different than what you saw on those other ones. Again, what you're looking at, the light part, is the event horizon, and it flows very quickly, and once something gets drawn into a black hole, it in fact becomes part of the black hole. There are lots of advantages to using satellites instead of permanent radio telescopes on Earth, as with the Event Horizon Telescope. In space, you can make observations at higher radio frequencies because of the frequencies from Earth are filtered out by the atmosphere. The distances between the telescopes in space are also larger. This allows us to take a big step forward, where we should be able to take images with a resolution more than 5 times that is possible with the EHT. Sharper images of the black hole will lead to better information that could be used to test Einstein's theory of general relativity in greater detail. The fact that satellites are moving around the Earth makes for considerable advantages. With them, you can take near-perfect images to see real details of black holes. If small deviations from Einstein's theory occur, we should be able to see them. The EHI is also able to image about 5 additional black holes that are smaller than the black holes that the EHT is currently focusing on, and so on and so forth. I think that kind of gives you the summation of what we have. And I'm open now for questions.
Ken, is my audio working now?
It is it's crystal clear.
Yeah, I just had to click a button and change the microphone input. It just took me 2 meetings to figure that out. So there was only one question that was posted so far in the chat, but please, everyone, feel free to post more. The question was about white dwarfs. When you were talking about how small and cool they're getting, the question was, are they not burning anything? Are they just cooling off, or are they still burning something?
They're still doing some burning, but the amount of burning that they're doing is really minimal as they cool. And of course, as they cool, they become, like we said, a rock, if you want to call it that way. Now, the gravity factors still work. There's a great example of that is if the sun were big enough to become a black hole, for example, or would become a white dwarf, that wouldn't destroy the orbit of the Earth. It would still be going around that area, that object, because the gravity remains the same. So people say, well, if it explodes, what's going to happen to us? Well, the fact of the matter is probably not a whole lot. But you don't have to worry about our sun going. By the way, it's going to become a white dwarf at some point. It will become a red giant, by the way, and that won't be good for us because it will destroy the Earth almost assuredly. The object will get hot, will be hot, and what it will do is it will expand out and certainly absorb Mercury and Venus, and will not absorb us necessarily, but could. And we have a couple of stars that are out there right now that are right at the edge. One of which you've probably heard about is Beetlejuice, or Betelgeuse if you want. It's Alpha Orion. It is a red giant. It is a hypergiant. A hypergiant is one that's very massive, and it is about at the end of its life. And we could be fortunate enough to actually see it explode. If it does, it'll be as bright as a moon. So it'll be very cool to see. But it's sometime between now and 100,000 years, so I don't know whether we're going to get a chance to see it. But a white dwarf, again, is just a dead star. Any other questions?
Got a few more questions coming in. I will say I had one that came in just directly to me. Callahan is with us. He's 6 and is one of our youngest viewers and was with us last time and is very excited you mentioned black holes because he had questions about them last time. So not a specific question, but he's just very excited about the black holes. So if you have anything to add on black holes, feel free.
Well, the black hole is a massive star that has collapsed, and it keeps collapsing, and it doesn't stop collapsing, and it gathers, and it's got tremendous gravity. And anything that ventures close to it gets drawn in and becomes part of it. It just flats against it. Now, I'm going to tell you something. What's his name, the young man? What's his name?
Callahan.
Callahan. Here's another thing that you want to know. If you get drawn into a black hole, by the way, time will stop. kind of weird, but the fact of the matter is that they say that if you were going into a black hole and you had the view, you could see the dinosaurs. You'd see all of time at one point. It would all stop. So black holes are very cool, but if one gets drawn into it, they get stretched right out and then they become part of the black hole. But kind of cool. Any other questions? Go ahead.
Yes, we had 2 related questions, I would say, about the expected life of stars. So one was, how confident are we in the science in terms of the expected life of stars? And the other was more specifically about our sun. Will it still be expected to be expending its energy in 5 billion years?
By the time that 5 billion years comes around, the sun will be gone. The sun has a life expectancy of another possibly 4 billion years. The likelihood that life will be on this planet is probably in the order of 1 million or 2. The sun is getting hotter, and but I have faith in technology, and I believe that eventually technologically we'll be able to change the orbit of the Earth. That sounds like far out there, but when you're talking about several million years of technology, You know, technologically, we're very, very new at this. I mean, we have not been able to do in the last 100 years, the things that we've done technologically are stunning. And if you had another million years added onto it, I think we could probably change the Earth's orbit and be able to let the Earth go on from there. What was the other question? I'm sorry, I got that one, but the white, you said something about the white dwarf that you asked.
No, the other question was just about how confident we are in the science in general of the expected life of stars.
This is my sweatshirt that says science doesn't care what you believe. All right. The fact of with science, the scientists are very good at what they do, and they know what they've done, and they know how to compare it to what else they're doing. There are, you see, the one thing that we've kind of put our brains into, and Einstein really, is the laws of physics. I'll tell you a very, very brief, humorous story about a senator that was before the General Motors research division, and they were talking about a car that was going to be propelled by another gas of some sort or whatever it was. And the scientist that was the one that was involved said, "I'm sorry." He says, "We can't build it because it's against the laws of physics." And the senator spoke up. He says, "A law? We'll just change it." You know? And he said, "No, sir, that's not how it works. The laws of physics are solid. They're unlikely to be broken." Now, that being said, if there was a technology that could break the laws of physics, then everything's out the window. But I'm of one of those scientific minds that say the laws of physics are probably constant throughout the universe. So there you go. That's how confident we are. A lot of people have been working on it. They're working at it all the time, and they're very good at what they do. And the laws of physics work because we try things. It doesn't matter what we do. If you hit something, it moves away. Laws of physics. Laws of physics guide whatever we do. We cannot travel faster than the speed of light. Okay? We can't do it because there's too much. It happens when something approaches the speed of light, something of mass, it becomes infinitely massive. So you can't do that. You can't get there. The universe, however, interestingly enough, is expanding faster than the speed of light. That's not the objects within it, it's the space itself. And nothing can move faster than the speed of light. Nothing can move faster than the speed of light. And we have a thing called dark energy that is pushing things out at an accelerating rate. Meaning that if you get into a spaceship and you're massive, have a certain mass, you ain't catching up with those other things that are moving away from you. And now, of course, we're talking at the galactic scale. We're not talking about the planetary scale or anything like that. Any other questions?
Oh, yes, there's many more coming in. Here are two related sort of theoretical ones about if the sun became a black hole or the Earth related to black holes. So if the sun were to become a black hole, would the Earth be sucked in? And the other question was, if Earth approached a black hole, would it be sucked in or would it orbit around it?
If a black hole formed at the middle of our universe and it was our sun at that point in time, we would still be revolving around it. We would still be going around it. It wouldn't draw us in. If we passed a black hole, we would be drawn toward it. Depending on our distance from it and our speed, would we be drawn into it? Maybe. Or we would be flung out more, depending on the orbit itself. So the point is, it depends on the proximity. So it's not like if the black hole comes here, are they going to grab us? Maybe, but probably not. Understand something about space. It's very, very, very large. Very, very, very large. I'll give you a good example real quickly, and then you can go to your next question. The Voyager One launched in 1977, I believe. Is that right? Was that about right? I think it was 77.
Same year I was born.
It just left the solar system, okay, from 1977. Traveling at 80,000 miles per hour, which is what it's traveling at, it will take another 1,000 years to get as far away from us as the next closest star, Proxima Centauri. At that speed, another 1,000 years. Okay, so nobody's been here or anything like that, probably, unless they can break the laws of physics. Okay, next question. Go ahead.
Going back to the life cycle of a star, from the initial gas cloud to the point where it becomes a white dwarf, what percentage of the star's life is in each of those stages?
That's a very good question. It depends on the type of star. Okay, so let's talk about that briefly. And I mentioned it briefly during the presentation. A big blue white hot star, very hot star, lives less time than a yellow star. So our yellow star's life expectancy is 10 billion years from start to finish. A star that is a red dwarf star, for example, could live several 100 billion years based on how much time it takes to burn the hydrogen into helium. A blue hot star like Sirius, for example, would probably live maybe 1 billion years. Super white hot stars like Deneb and Rigel have 1.5 million to 2 million year lifespan, because that's how long it takes to burn up all the stuff that it has. So the life cycles are different. The cooler stars live longer, lots longer than the white hot stars that eventually become supernova or black holes.
Do most of them spend the bulk of their life in that main star phase, though? Or are there some that would be a nebula for a really long time first? And then I guess that's still, you're saying it still depends on the size of the star.
And with the nebula, again, let's take a nebula, for example, the Crab Nebula, for example. Crab Nebula is expanding right now, but eventually it's going to start coming back together again. Okay? That was a super star. Now, remember what we talked about. What are humans basically made up of? What's the basic chemical? Carbon. Okay? Carbon is the only element, and the elements don't change throughout the universe, by the way, if you don't include dark matter and everything like that, which is a whole different story. But matter is the elements that we know. And the elements start out just as hydrogen and a little bit of helium. Big Bang probably produced a 24% helium presence in the universe, but that's another story again. But again, the other elements, the heavy elements, had to be created in the middle of collapsing stars, and big ones, okay? And in the very beginning, they were really, really big. And you produced this stuff, and eventually, at first, the matter that was there wasn't directed to one and other pieces by gravity, but by electromagnetic movement, okay? And that's what started to draw them. When they got big enough, they started to get gravity. And as they got gravity, they started to combine with other things, okay? If you notice that most of the things in the universe that you look at, planets and so forth, are round, have you noticed that? All the stars are round, all the planets are round. When you get to a certain size, everything pulls together into round. If they're smaller, they much smaller, they can be like rocks out there in different sizes. But big ones eventually do that. Now, what happens is when the gravity pulls together all this stuff that keeps controlling like this, if it gets to be a certain point, it ignites. The hydrogen starts to burn at that point in time, if you want to call it that, but it starts to merge, okay? And then you've got a star. If it gets not big enough, it becomes an Earth or a Jupiter, which doesn't have electromagnetic field, but it doesn't have doesn't have thermonuclear reaction. It's not big enough. It needs to be a certain size and mass in order to produce thermonuclear reactions. Thermonuclear reactions, again, like the story, pushes it out. Gravity pulls it in. And that's how it works. So as long as you're turning hydrogen into helium, you've got an object. Once that hydrogen is gone, gravity takes over.
So I think you sort of just answered a question that somebody put in the chat, but just to make sure that it's explicit, they were asking about why a nebula would come back together. So essentially, if you're saying there's a force when it explodes, there's a force pushing it out, but then there's gravity in the material that's left behind, and it eventually is pulling everything back into that gravity.
Understanding that gravity rules and electromagnetic rules at the smallest levels, okay? So for example, if you pick something up that's metallic and it clings to something else, that's electromagnetic field. Okay. But if the Earth and the moon, that's gravity that keeps it in orbit.
Here's a fun one. Somebody, another one of our young astronomers, wants to know if there is a star that can be rainbow colored.
That's a really great question. Good for you. Actually, all the stars are rainbow colored. Okay. Let me explain to you what I'm talking about. Light breaks down, and visible light can be scattered, right? This is a great question. Great question this person asked. The rainbow. What's the color of the inside ring? It's blue. Okay, that's why our sky is blue. Okay, the reason the sky is blue is because light breaks down into the visible spectrum, and the inside ring is blue, and that's the shortest waves. The shortest line is the blue line, as opposed to the red line, which is on the outside. So what happens is the atmosphere is about 90 miles high, straight up, okay? And the sun is a yellow star, but it wouldn't make any difference. What the sky is blue because the blue lights get scattered when it comes through to us. So that's why the sky is blue. What happens to the sun and the moon when it's at the horizon? What color does it get? Orange, yellow, right? Orange, red, right? Okay. Because the last waves that get through are the red light, which is the longest waves. And that's why the sun and the moon and even the stars take on a reddish hue as they get to the horizon, because that's 1,000 miles of atmosphere as opposed to 90. So the light gets scattered. Anybody seen a lunar eclipse? What color is the moon? It's red. And the reason it's red is because the last lights of that spectrum get through the atmosphere. As it goes through all the atmosphere of the Earth, it gets scattered. So the only light that's left that falls on the moon is the red light. So that's why it's red. Good question, because it sparked something that a lot of people don't understand, but there you go.
All
Next
right.
question.
These are a little more complicated.
Go ahead.
As a star, I'm just going to read these directly. So as a star nears the end of their life and blows off the outer layers, is there enough hydrogen left to seed more star production?
Yeah, there is, depending on the size of the object.
Okay. And then this one says star production areas like the pillars of creation are visible because of the non-hydrogen elements. Are lots of other elements attracted by gravity, and can they still produce a sun? So there would be something like a dirty sun.
Yes, well, we're a dirty sun. That's a good question, because the reason is we have all those elements. We are the result of another star producing all those elements that gather together. We are sometimes considered a third generation star stuff. That's what we are. The reason you live today is because you're carbon based. You couldn't be carbon based if it wasn't produced within a star at some point in time. When it get together, our sun is very rich in the other elements as well as being hydrogen and helium. It's the big white stars that only have hydrogen and helium, generally speaking, and that's why you're unlikely to have planets going around them that would be rich in the other items, but it could happen. Does that answer that question for you?
Yeah, I think that's a good one. This one says, if a star as big as the sun replaced it in the same situation, would life on Earth be close to the same? So I think that's a speculation about formation of life around other stars. And
okay, I love that question. This is becoming great fun for me. All right, here we go. Life elsewhere in the universe. My attitude is it's endemic. It's everywhere. Okay, but it's not like Star Trek, and it's not like Star Wars. The fact of the matter is you are 50% of your DNA is exactly the same as a banana. All right. We are the result of biological accidents over a period of 5 billion years. Biological accidents produce life forms that differ based on what the environment is. For example, let's have another planet similar to us in size, has water and everything on it that we need, but it has an average temperature that is 10 degrees higher than it is here, okay? Or 10 degrees lower, or 80%, let's make it 40% oxygen as opposed to the amount that's on the Earth. All right. 1 second. Let me just shut that. Sorry. Okay. Good. All right. So the point is that life forms will form to the environment. The environment on the Earth has changed also, so that humans have been here. Well, let's take the Homo species, probably a million years. Humans about a Homo sapien about 125,000 years. Talk about 65 million years ago, there were dinosaurs on this planet, and to about that. And those were formed because of the environment as well. So what happens is that if there's mutations like that on a planet, what you will get is you may have something you wouldn't recognize as it could be carbon-based, but you wouldn't recognize it. It wouldn't walk up to you and talk to you, is what it is. And then, of course, you talk about the social issues of parenting and political things and all the other things that go into what our civilization does, as opposed to what a civilization was completely different than ours. Maybe they're vegetarian things that walk rather than mammals and reptiles and everything like that. We don't know what it's like over there. That's one of the reasons why it's difficult to understand why anything would travel here, get to the technological end to travel here, because they'd have to evolve a certain way in order to do that. Take a planet that is entirely water. You can have species on that planet, but are they going to get out of the water and take a spaceship out? We don't know that, do we? So I'm very highly skeptical about being visited, but life is endemic in the universe at one form or another. Okay, does that kind of answer that question?
I think so.
Okay, and you also have the balance of what the organs are made up of, a little bit different. You don't know. A plant isn't a human, is it? Right? Well, okay. Go on.
There's a clarifying question from the person who asked about the pillars of creation and the idea of dirty stars. And they were trying to ask, okay, let me read this again. For example, in the pillars of creation, there's much more in there besides the hydrogen. So do stars selectively form only out of the hydrogen, or can other elements be incorporated into a star as it's forming?
Again, what I'm saying is that's usually what the later generation stars are formed. It isn't. Hydrogen is the igniter, okay? But there's elements like crazy in those things. But understand that you don't have to, when you got something as big as a star, you don't have to have a lot of it, okay? You have mostly hydrogen and helium in the stars, okay? Mostly. But you can have as much as 5% of the matter in a star could be all the other elements, and that could be a lot of stuff, okay? So when you have the objects that are outside of that star, have you ever looked at the difference between the comparison between the Earth and the Sun, for example? A moderately small star. We're so tiny, we're a speck. But all you need is a little bit of that stuff in the makeup of the Earth in order to produce all those other elements. So yeah, our star has lots and lots of oxygen, has lots and lots of hydrogen, volume-wise, but not percentage-wise. You understand that? Okay, the percentage of the star itself is going to be around 95 to 99% hydrogen and helium of all the combined. Again, I'm not taking putting hydrogen and helium as one. Okay, most of the star is going to be hydrogen and helium, but that small percentage, you've got a planet by the name of Jupiter. That's 86,000 miles in diameter. I'm almost embarrassed, I know that, but 86,000 miles in diameter. Okay, if you take a look at the makeup of Jupiter, it's got lots of elements in it. Saturn has lots of elements in it. and there's a lot of hydrogen and a lot of helium. Now, here's the problem with it. Ever had a helium balloon or a hydrogen balloon? Where's it go if you let it go? Where's it go? It's leaving. Hydrogen leaves a planet our size. It doesn't stay because our gravity can't hold it down. A star, no problem holding it in, right? Planet Jupiter has lots of hydrogen and helium in it, lots of it, but it's not big enough to ignite. So you can't have thermonuclear reaction in a planet, even a big planet that can't produce the thermonuclear. If the Jupiter were 15 times larger, it might be a star. We might have a double star. Does that answer that question?
I think Ward said, thank you. They now get third generation star forming. So
You absolutely
yes.
can. Absolutely no question about it.
Do you know what is known about quasars and how they relate to black holes?
Okay, well, quasar there's none of them that are close. They're all way out there. And a quasar is an object that has all the elements that you have in a star and so on and so forth, but it's a forming star. And quasars are not close to us. They are way back in time and way way far away. I don't think there are any active quasars. There could be, but I don't think there are any active quasars in our universe today. What I'm saying is those quasars that we are looking at are long gone and have produced something else afterward. So what we're talking about is, again, we're looking at quasars at the distance of about 12 billion light years or 10 billion light years, 10 to 12. That means the light started from them 10 to 12 billion years ago. And I don't know. Again, I do not believe there's quasars that are extremely active in our known universe.
All right. I missed a question I wrote down.
Go ahead.
Are red dwarfs implied to be first generation stars due to their 100 billion year lifespan?
Yeah, they're generally red dwarfs are generally stars that are formed early on and are still existing. So understand that if you look at the periodic table, which is another thought process that goes with this, the stars that are red dwarfs don't burn very long. I mean, burn forever because they can't burn up all that the stuff that's in them. It just takes too long for that to occur. And when you move down to the bottom of it, there are 14 times as many M stars as there are K stars, and 14 times as many K stars as there are G stars, which is us. And there's 14 times more G stars than there are going up right on up to O, B, and A. So the percentage is enormous of the amount of red dwarfs that are in the universe. They outnumber everything substantially. Okay, that's a big thing. We are much more common than a white giant star, an O or a B, and that's the way it works.
I see one more question. If I've missed any, everyone please tell me. What is the reason behind the dark appearance of the night sky?
What is the reason behind what? Say that again.
The dark appearance of the night sky. Like, why is it dark at night when there's all these stars out there?
Well, the fact is the stars may emit way more light than our sun does, but they're so far away, we don't get them. So the object that lights our planet is the sun. And when we're turned away from the sun, it's dark because and understanding that a lot of the light that we get on the sun side of the earth is also the light that is scattered by our atmosphere. Okay, but it doesn't get scattered around the back. It just scatters in the area, and that's why you get a nice big light star. Now, if you didn't have if you didn't have any atmosphere, the sun would look a whole lot different. It would just look like a very, very bright object in the middle of the sky. It really wouldn't light us up very, very well because the light wouldn't be scattered again, the light would be just from the sun.
We just got one of my favorite questions just popped in. I'm going to find the video link to share when you answer it. But if everything in the universe is moving away from everything else as the universe expands, can Andromeda actually collide with the Milky Way?
Very, very likely will collide with, and as a matter of fact, in about, I think it's 2 billion years, it will collide with ours, and we will become one galaxy. It will collide with the Milky Way, no question at all, and we will become one galaxy.
There's some really nice models out there showing what that will look like and how there's so much space in
Very
between
cool.
all of the things that we won't actually like feel like we are crashing, but we will
By the
melt.
way, the Large Magellanic Cloud is going to collide with us sooner, by the way, but that's not going to make a big difference. But
Okay, I posted a link in the chat to one NASA video. I didn't get a quick chance to look at this, but you can definitely Google collision Andromeda and Milky Way and find some nice models.
very, very cool. You know, and it won't affect everything. Here's the interesting thing: how many stars do you think would collide when they collapse, when they could go into each other?
I'm gonna get 0.
Zero is probably the closest number.
Oh yeah, 2 other people said none. Yep, everyone's saying it.
Yeah, and the reason it's none is because of the fact that, you know, a star is like a truck in Detroit and a truck in California. Are they going to ever collide? And that's what you're talking about, distance between stars. So it's not going to happen. Maybe once, you know, maybe the one affects another one, but even with we have 200 billion stars or something like that in the Milky Way, and there's probably 400 billion in the others. They're not gonna run into each other, I don't think. My opinion, but again, I've never been always right.
No, we won't be here to find out. But
That's for sure. Yeah, that's the one thing we know.
I think that was the last question in the chat. Those were great questions. This was really fun.
They were great, and I hope I answered them. And again, like I said, there are possibilities that we'll find things that some of the things I said may turn out to be not quite as true through time, because that's the way it works.
Well, thank you very much, Ken.
And thank you for having me. I have enjoyed the heck out of it. Great questions, by the way. You can applaud yourselves, by the way. Great job.
Thank you. This will be put on our YouTube site. I can't promise how soon it will be, but usually it takes close to a week, sometimes later. We also, I try to schedule the astronomy programs on the 4th Tuesday of each month. And obviously, given this is a Wednesday, we change that schedule when it's necessary. Next month's program will be back on the 4th Tuesday, June 28th. The Eventbrite link is not yet published, but it will be soon. If you received the link to tonight's program from an announcement, you should get another announcement for next month. You also have the option of subscribing to the library's newsletter or following me on Eventbrite. Not that I am looking for followers, but it is effective. Let's see, do I have anything else? Anything else anyone would like to ask? We can unmute people if you'd like, but it looks like people are starting to go away, which makes sense. But thank you so much, Ken, and thank you, Megan.
Yeah.
Always appreciate your help.
Ken, you got lots of thanks in the chat, and I was supposed to tell you, but couldn't because I was muted earlier, that Mark Christensen says hi. He was sorry he couldn't make it.
Oh, yeah, I like Mark. Great guy. Okay.
Yeah, he had a family thing. I'm going to see him tomorrow, but he says hello.
Give him my regards, please.
Yes.
Great
He
guy.
plans to watch the YouTube video, so.
Well,
Whenever it's available.
well, April 9th of 2024, I'm going to be in South Mexico to see that eclipse, where it's the probability of seeing it, you know, better than Cleto, which if we got lucky, we'd have it here, but
nice. Take good pictures and then come share them with us.
If you like the weather in Michigan, wait a minute. Thank you again.
Okay. Thank you.
We'll
And
catch
I
up.
think we will end up now. Good night, everyone.
Right. Thank you, Jennifer. Appreciate it.
Thank you, Ken. I
And
really
Megan
appreciate it.
Take care.
Great,
Bye-bye.
great presentation as always.
Oh, thank you. Bye-bye now.
Goodbye.